Have you ever wondered what really goes on inside a computer? How does a program know it's a program? How do the button presses on a keyboard get turned into letters? How does a hard drive know what it contains? If so, then you're in the right place. Welcome to Hello World. What even is a computer? These days, the term is muddy at best, and trying to come up with a clear distinction left me wallowing in jargon. So for this series, we're using it as a blanket term covering any electronic device upon which a user can install and run software. As for what constitutes software, well, we'll get to that soon enough. Every computer, from your shiny new laptop to that smartphone with a cracked screen you bought secondhand online, is a miracle of modern technology that we take for granted. Stop to think about it for a moment. You can summon music and videos from the air. You can communicate in real time with people thousands of miles away. You have the entire wealth of humanity's knowledge available instantly at your fingertips. And somehow, we've all forgotten it's amazing, because it just works. You don't need to know how a hard drive works to store your files on it. But if you knew the hundreds of things that have to go just right, every time you ask your computer to do something as simple as pulling up a web page, you would be amazed. My hope with this series is to give you a simple explanation for these complex systems that your computer and phone use to perform these daily miracles, in the hopes of deepening your appreciation and understanding of these ubiquitous devices. Now you might think miracle is being a bit overdramatic, but think of it this way. How far back in time did you have to go before people thought you were a literal wizard for brandishing even the simplest smartphone available today? Remember that the first cellular phone only came out in 1985, and all that did was make phone calls. Digital cameras weren't commercially available in the US until 1990. The earliest digital audio encoding was developed by Bell Labs in 1950, but the MP3s your phone plays relies on an algorithm that was proposed in 1987, but the processing power to make it work in real time wasn't even widely available until the mid-90s. So even if you took that algorithm back in time, the fastest computer of the era wouldn't be fast enough to play a song in real time. And let's say you live in 1983 and you wanted an MP3 copy of that year's greatest song, Walkin' on Sunshine. A hard drive with the 3 megabytes of storage needed to hold that single song would cost you $1,000. Each of these features is a miracle in its own way, but at the risk of performing some light heresy, even the word miracle undersells technology for one big reason: consistency. Technology follows internally consistent rules. By this, I mean that if all input factors are identical within a given tolerance, the output will be too. If you and your friend each have a copy of the same text file and you each open it up, you'll see the same result. The tricky part, as we'll discuss in future episodes, is that these input factors I mentioned previously are innumerable. Ambient temperature, elevation, even physical position within a room can affect various aspects of your computer or device's performance. So, although technology follows rules, we do still perceive some inconsistencies due to inputs that are difficult to understand or control. But who or what sets up these rules? Some of them are matters of physics or chemistry, such as the physical proximity of components on a circuit board or the conductivity of gold at a given temperature, but the rest is defined by the software itself. The software makes its own rules, bound only by the physical limitations of the device and the programmer's imagination and skill. So how does it make these rules? Well, I'm getting a little ahead of myself. Let's take a few minutes to get everyone on the same page of understanding about the concepts we're about to discuss. Many of these concepts are only going to be touched on at a surface level in this episode, but subsequent episodes will cover them more thoroughly. Firstly, what do we mean when we say computer program? A program is a set of encoded instructions that allow a computer or other device to convert human intent into actionable logic. The web browser or app you're watching this video on, the games you play, and the bundled launcher you need in order to download them, the image editor you use to make memes. Those are all programs. The encoded instructions that make up a program begin their life as code, written in one or more of a plethora of programming languages. A programming language works much the same way a spoken language works. It's a specific ordering of symbols that allow for a shared understanding of anything the language has the grammar to describe. This is a fairly large subject. We'll cover how these work and the programs you use to make programs in a future episode. But often the first program you learn to write is one that simply prints "Hello World" on the screen. Programming languages aren't spoken, of course. They're textual. That means we need to have some way to speak to the computer. And while our smartphones' digital assistants can do some neat tricks, the technology just isn't there for the necessary syntactical nuance required for anything other than single-sentence SMS responses. So, historically, interfacing with the computer has been made possible by various human interface devices. That just means keyboards, mice, the touchscreen on your tablet, etc. They all serve to communicate with the computer, ideally in the least ambiguous way possible. Future episodes will elaborate more on how the most common devices function, but for now it's enough to know what we mean by input devices. That covers how we talk to computers, but how do computers talk to each other? Much like we have languages to talk to computers and to each other, Computers have a few different protocols for talking to each other. A protocol is just a set of rules that describe how data is packaged up for transmission and how the data should be handled when it's received. The behavior and functionality of these protocols vary, but we'll cover that in a future episode. One key aspect of networking protocols is that they allow computers with different operating systems to communicate. The operating system is the unsung hero of the software world, the giant sprawling mass of code that handles the tasks that most users don't even think about, and programmers generally don't want to have to deal with. Raw disk access, device management, user management, and so on. OS X, Windows, Unix, iOS, Android, Mac, they're all operating systems. The operating system is the very bedrock upon which the programs are built and the gateway to the physical realm of hardware. By hardware, I specifically mean the stuff contained within your phone case or desktop tower, the circuit boards and resistors that perform your device's most fundamental communications. Even though most programs do not talk directly to the hardware, hardware can affect program behavior. Programmers often need to be aware of the differences in hardware between similar devices, despite having the operating system to act as a buffer. For example, even though most modern smartphones have a gyroscopic sensor to determine which way is down, the values that a programmer receives when they ask for down can vary a huge amount between operating systems and even device models. Okay, that was a huge amount of information, and we haven't even scratched the surface of what this video will cover. If you need a breather, now's a good time to pause. I'll wait. Alright, back and feeling refreshed? Good. Earlier I said that a program makes its own rules to follow, and a little later I said that programs are a set of encoded instructions, so let's start there. The rules are defined by these coded instructions. Each instruction tells the program what to do based on a set of inputs. The more consistent and careful the programmer is when making these rules, the more reliable the program will be. For the examples that follow, we'll be talking primarily about the Windows operating system because it's the one I'm the most familiar with, but the broad concepts are the same across all operating systems. Executable files on Windows-compatible systems usually have an exe extension. If you open up any arbitrary executable file with a text editor, you'll see gibberish. Sure, there are some letters and even occasionally some recognizable strings, but the rest are just large spaces of nothing. This is due to the encoding. The program on the disk is stored in a binary format of ones and zeros, while the text editor is doing its best to show you the binary instructions in the format it thinks you want, letters. Of course, the binary in the file is not intended to be mapped to letters, so there are going to be big gaps, and depending on the editor and font, use squiggles and shapes, some familiar and some not. To understand how computers encode things, we need to understand binary. And to understand that, we need to start with a decimal encoding. Don't worry, you already know how that one works. Believe it or not, this is a number in decimal encoding. When you look at the number 203, your brain does some math to decode it. It counts up the digits and assigns special values to each of them. Depending on where 2 is, it can be 2, or it can be 200, 2,000, 2 million. Even the 0 in the middle, it doesn't mean nothing is there, it just means there's no tens value. We have 10 digits to choose from, so each digit position heading leftward indicates an increase by a factor of 10. So in a flash, your brain looks at the digits and says, okay, 3 plus 0 times 10 plus 2 times 100 equals 203. The difference with binary is that we only have 2 digits to choose from. Each piece of binary data, which are called bits, is either a 0 or a 1. That's not much information, so like the decimal encoding you've been using for the better part of your life, we group them together. Likewise, since each bit can only represent the equivalent of 2 digits, the bit's position heading leftward indicates an increase by a factor of 2. We take the same formula we did before, but now your brain has to do some math we're generally not accustomed to. The formula is now 1 plus 1 times 2 plus 0 times 4 plus 1 times 8 plus 0 times 16 plus 0 times 32 plus 1 times 64 plus 1 times 128 equals 203. The fact that binary uses powers of 2 allows us to do some cool math tricks. For example, when you see a number written down in our top secret decimal encoding, you can easily multiply it by 10 by shifting the digits to the left and sticking a 0 on the end. It's just as easy to multiply by 100 or 1,000. It's because, like we said before, each digit represents a factor of 10 increase. We say the system is base 10. Binary is base 2, so we can do the same trick to multiply by powers of 2. By shifting digits to the left, we can multiply by 2, 4, 8, and so on. In fact, we even call this operation as left shift in computer science. Similarly, you can do division by the same factors by shifting the bits to the right. There are more cool things we can do with bit manipulation, but that's for another video. Binary, as you may have noticed, can be hard to read even now that you understand it, so let's talk a little more about encoding. It's another system you're already familiar with, though possibly not by name. Let's say you've got a byte, a string of 8 binary bits put together. This allows us to depict 2 to the power of 8 numbers, anything from 0 to 255. That's all well and good, but most humans communicate information with letters, not numbers. So let's map some of those numbers to letters. The English alphabet only has 26 characters, so we can have uppercase letters, lowercase letters, digits, and even a few assorted punctuation marks with plenty of room left over for anything we want. Even some squiggles, like we saw in the executable file earlier. This is what ANSI, or the American National Standards Institute, did when they invented the first modern character encoding scheme, the American Standard Code for Information Exchange, more commonly referred to as ASCII. The first version of the ASCII encoding standard was published in 1963, and although it went through some revisions, it remains one of the most common mappings for English text. It uses only 7 bits, giving it 2 to the power of 7, or 128 entries, but as we saw earlier, that's still plenty for English text. I've been throwing around the qualifier English text because for languages with larger character sets, you'd have to use an encoding that allows for a greater number of possibilities, like UTF-8, which allows you to have 2.1 million characters compared to ASCII's 128. Your emoji choices back in the 80s were rather more limited. But that's all human-readable stuff, which is not what we saw when we opened up that exe file. Let's go back and look at it again. The text editor was showing us text because that's its job, and those squiggles, those are special characters that represent non-printable concepts such as delete, backspace, character return, or line break, the thing that happens when you press enter. The same binary data can be represented in multiple ways, so if we open this same file with a hex editor, we'll see something quite different. Okay, maybe this doesn't look any more human-readable than we saw before, but it gives us some insight into how the computer sees the program. Each of these chunks is a hexadecimal byte. Hexadecimal is another encoding method and a very common way of depicting a program's innards when we don't have the source code available. What you're looking at here are the instructions that tell the computer what to do. Each of these bytes corresponds directly to an instruction to the CPU. For more on that and hexadecimal encoding, please join us next time as we explain what assembly language is and how letters on a screen get turned into those instructions. Thank you for taking the time to watch our first episode. If this sounds like a series you'd like to see more of, please subscribe below and click the bell to be notified as soon as new episodes are uploaded. If you know of anyone who might enjoy this video, please send them a link. And lastly, please write a comment below if there's anything you feel we missed in this video, or if there's a subject you'd like us to go into more detail on in future episodes of Hello World.